So Abdullah, how many registered total?
How many what?
How many are registered?
178 we have.
Oh.
Yep.
Maybe all are on YouTube, maybe.
Yeah, we're live now. And now we have started the webinar.
Yes. We'll wait about 5 minutes, gents.
Okay.
And we'll start the talk of the today. So nice building view is it's a presentation slide.
Yeah, this was actually one of the very first ones. I mean.
Oh, okay.
So
nice.
No, I mean this project is highly architectural driven. I mean that's going to be a lot of my topics. I mean.
Okay, nice. I can see that.
So
it is a view from the other side of the Burj Khalifa, you know.
Yeah, from the Al Khail side, Al Khail Road side.
Yeah. Good. Another 2 minutes, we'll start, Jens.
Yeah.
Yep.
The road around the building is completed, I believe now.
Yes, it is. You can actually drive on that road and get in.
Yeah.
But it's typical to buy a lot of these projects. I mean, I was down at this Avenues Mall yesterday, and next to there you have this ICD Brookfield, right? And I drove into that, and you couldn't get out again because all the road is not finished yet. I mean, GPS said go in there, and then I had to back out again. And everybody is saying that it's finished, but it's actually not finished, right? Because the roads are crap around there. I mean, I thought I could drive that way in, but yeah.
GPS is not updating regular, you know. Maybe the frequency is
always a little road work here and there.
I think we'll start maybe. Yeah.
Yep.
Yeah. Good evening.
Now we're live on YouTube. We're here. We're ready. So everything is settled.
Okay. Yeah. Good evening, all of you, and we welcome you all on behalf of Institute of Structural Engineers for today's CPD talk. Myself, Sama Srinivas, Chairman of the UAE Regional Group, and Mr. Abdullah, who is our Secretary of the region. And today's speaker, Mr. Jens Fussing, who is a well-known speaker and well-respected engineer. And he has got he has got 20 years experience in structural engineering. he worked around many countries. His works are presented in maybe more than 24 countries. And he has expertise in high-rise structures and specialty in precast systems. And his passion is mentoring master's, PG, and PhD students. Welcome, Mr. Jens, for accepting our talk today. And today's session, in principle, we are on Zoom platform, and we're on YouTube as well. You can see, we can take up the question and answers at the end of the session. You can post your questions. You can see at bottom of your screen probably, and then we'll take up the questions at the latter. Yes, that's all from my side. And Jens, platform is yours.
Yeah, thanks for that. Thanks for having me again. And this year 2020, where it's been a little bit disruptive, everything. Yeah, I'm going to talk about this building today, which is located in Business Bay. It's called the Dorchester. And when you look at that screen there, the building is about 150 meters long and it's 150 meters tall. So it's almost the same proportions up and what do we say in the width. It's partially, so from this view here, the right side is the hotel and the left side is the hotel apartment side. And the main stakeholders is it's Omniat, who is the developer. And the original architect was, still is, Foster's and Partner. And the contractor is Roberts Construction. So if we take a look at where it's located, you can see on the screen here that we have Burj Khalifa. And then the plot is a little bit base shape, round shape. You can see it over here. And everything is about maximizing the view against Burj Khalifa. So the building actually has a kink in the middle. It's like it's bending around the middle axis of the whole building. So I rejoined BG&E in actually 5.5 years ago. I came back to Dubai, and one of my first projects was called Plot 18, amongst a few other projects like Aloft and N1R. But this one was one of the biggest one where we had to develop the concept. And it's located in Business Bay, but it's under Dubai municipality, and it also has a third-party review process on top of it. And as all other projects here in UAE, projects change names. Right, so first it was called Plot 18, then Seven Gardens, and now the Dorchester. The Dorchester is the hotel operator. That's why it's called the Dorchester. Just one thing, I'm going to go a little bit back and forth, but a lot of the things is related. I'll come back to this later. If you look at down the middle axis here and the bottom axis, you'll notice that the building is open. It's very open. It also has a lot of open structures, open voids here in the bottom. We'll come back to that when we touch on wind engineering in the middle of the presentation here. It's very important to just remember this as we get closer. So doing a concept. My first view of this building here was that it was like a sky bridge, right? I mean, you could do this as steel structures, these portions here, and then you could do some fake columns. A little bit like other sky bridges we've been involved in, other projects around the world. So that was the concept I had in my mind, but that was not what Foster's and Partners wanted. They didn't want any fake columns. A column had to be pronounced, it had to be expressed. It's actually part of the whole architectural intent that you can see these columns, which of course is important to understand as an engineer. So these columns here are 30 meters tall. And in the beginning they were like 500 millimeters thick. So of course that didn't work either. We'll come back to that. So if we see what what the usage actually is. So now we see it from the other side. So the taller portion is the hotel apartment, and the lower portion is the hotel section of the tower. If you notice, you can see the floor plates do not line up. So the floor plate in one building does not line up with the floor plate in the other building, only at this level here at the roof. So underneath here, there's two common basements. Then we have all the common podium structure in the bottom here. There's a ballroom over here. You can see that 1, 2 columns are transferred out. We'll come back to that in a minute, and why that is. And then up top here, you have a pool and a sky bar. But one thing which was important for the architect was these 3 things, which was holy, very holy. I mean, the voids, the way the voids look, why they were there. We'll come back to that with some photos later on. The column are being expressed, and then also the facades, the way they look and the way they're designed and the way they shade. Those 3 things were extremely important to understand what was going on architecturally. So if we just look at it, the hotel apartment is 136 meters tall, and the what's it called? The hotel itself is 125 meters tall. So that's sort of the proportions of the whole building. And the few transfers which are there are done with V-shaped columns and raking columns like that. And we'll come back to that also. There's a few slides how we did that. So this one here is the layout of the building. You can see that it has like a kink. It follows around the same shape as the harbor front. If we look over here, you can see the ballroom. And if you follow the tower footprint, you will see that, oops, where are these 2 columns? They're gone. And then of course the floor plate goes back, the footprint goes back here again. This is one of the extreme challenges, to move 2 columns in the bottom of a tower footprint. And then if we go back a little to the so here in the middle here, again, an architectural and structural challenge is that you have drop-off zones. All these columns here goes straight from foundation to top. They cannot be touched. It's a holy. It's what should we say? It's an architectural impression which has to maintain like that. This little stairwell, we'll come back to that also, why it is there. Architecturally, it's in the way. Structurally, it's extremely good to have it here. Again, you can see the footprint of all these round columns. Those are the footprint of the tower itself. Let's go back again. So those are sort of the challenges we can say with. So how do you make sure that all these columns can go all the way up and only sit in the division between the hotel rooms when you have a shape like this, and you have all these things going on here in the bottom with drop off from one side, drop off from the other side, a stairwell here, a ballroom over here. These are sort of the extreme challenges we have, but you can also see that how open it actually is here for wind to flow through. There's a lot of openness in all this building here in the bottom. See, this is actually tower columns you have over here. So wind can actually flow through all this area here. And as I said, we'll come back to that. But the building itself has a funnel shape. This is the predominant wind direction because the Gulf is out that way. And that's where the strong winds come. If we look a little bit about on the architectural floor plans, this is just one of them. But here you can see that this is one void, and then you have columns in the middle here, and it's all rounded. So we have nice round edges in the voids. But it's of course a huge puzzle because when you look at how everything is laid out in the beginning, there are requirements for room sizes. There are requirements for how many rooms are you going to have, and all the columns needs to line up. That is a puzzle. You can see how it shifts to the other way around. So now we have the void in the other side of the building, and still the same columns must go straight up and down. So it's not like a sky bridge. It is like a building, but with no facades where we have the voids. That's the way it should be looked at. And if we look at it from a structural point of view, it's the same levels I have taken here, but you can see how it looks with the structural framing, how how the column changes over. So for example, this column here, if you say column number 11 sits on column 11, and you will see here it's a blade column, and here it's a circular column. We'll come back to how that is done. And of course, in the beginning of the concept, the cores are not that big. The cores are, of course, smaller, and they grow and they grow and they grow until you find all the right stairwell sizes, MVP, elevator number, all that stuff. So that's part of the process. I will just touch a bit on these facades. The facades originally Foster's and partner wanted to do these facades and balconies in prefabricated, and I agree to that opinion completely, of course. And I'll come back to why right now. So if you look at it, you have fins, which are all the same. You have balconies, which are all the same. You have facades, which are all the same. An insane amount of repetition factor. So much industrialization is in this view here. So the way it had to look was like white concrete or GRC painted white or something like that. And then you have this balustrade, which is raking and also creating shadow for the sun, so you don't get that much direct sunlight into the room, which of course is a sustainability thought. But when you look at this photo, this rendering here, it screams modular construction. It just does. But no, when decisions are run by commercial people and not builders, when I say commercial people, I mean UAE builders. So they wanted to do it traditionally, where they cast the slab out. You put insulation, you put membrane, you clad all that stuff, and then you erect your facade, and then you put your balustrade on afterwards. Also, as a key number from what should we say, from CTBUH, as just a key number, you can do the math. A rectangular building has the highest facade to floor plate ratio, as opposed to, for example, a round building. You can just make a building which is 300 square meters, and you can do the math. So therefore, the facade is expensive because the building is rectangular. So that you cannot change. But what we heard was, no, it was impossible to make it prefab because nobody knew how to do it, and it was very, very difficult, and it was impossible. And this was the commercial people who said that, and not builders. I just want to show some ideas. I mean, the wheel is invented already, right? You have systems where you can, where you have fully thermal broken, what should we say, facades, balcony systems, where you can make a balcony, which is even, of course, more slim because it doesn't have all that bulky. Because now you need to build in membranes and insulation and all that stuff. The wheel is already invented. It's out there. It's not rocket science. This is from North Europe, and it's a fully thermal broken, what should we say, type of balcony systems. See, this is some other systems where you can see here the brackets are ready to receive the balconies, and here is also a thermal break in here behind. And when these balconies are erected afterwards, there's no membranes, there's no insulation. All that work process is, you don't need to do it. Whereas the one we have chosen now is very slow to build. So this, I just want to keep on touching on this. And this is a project we've been involved with for the last 3 years, where we've been helping a developer in Denmark together with Big to develop a tower project, which goes from 20 meters up to 100 meters. So it's mostly the structure, but also the facades and the balconies. So the way it should have been done was that you have a structural system, then you have your curtain wall, and then you have your balconies afterwards. That's how it should have been done. And then, of course, no thermal break Of course, no thermal bridges either. And when people tell me something is impossible, look here. What are they saying? Is it not impossible? Possible. See, you have the same thing here. You have the fins, which we had on the Fosters. We have a raking, what should we say, a raking balustrade. All of that is done here. On these towers here, we only have 4 different types of, what should we say, balconies. So on this tower here, each facade takes 2 weeks, 2 days to erect. There's 16 numbers. It takes 2 days. Each balcony takes 2 days to erect per floor. If you look at it out there right now, right, it takes an insane amount of time because you have cast-in steel, post-tension slabs. You must put insulation. You must put membrane. You must put your GRC cladding. Then you have to put your facade in from outside with a counterweight. Then you have to put on your GRC on your balustrade, and so on, and put the lights. So we still have a lot of improvement to do here in UAE, and this is why it's fun to do these talks, because it's always about going back and forth. The structural system, which is on these towers, is actually ideas I have from here, from Dubai. So it's always fun to when you can mix these ideas. But to me, this project and what to say, the Dorchester on this project I'm showing here has so many similarities when it comes to facades and balconies. And the wheel is invented. We don't have to build slow anymore when we do balconies and continue the floor plates out. Okay, now to the fun, all the structures. This is not to be sarcastic or anything, but I call it the Bumble Bee because it shouldn't fly. When I say it shouldn't fly, of course you can always make a building fly, but it's meant in a positive way because we have challenged so many engineering principles on this tower here, first principles. For example, okay, the structural system is a hybrid system. We'll come back to that. First of all, the floor plates do not line up. Usually when we have diaphragms, we would like that the floor plates sort of meet each other at some locations. No, they don't do that here. The hotel rooms, the column grid is 9 by 11 meters. We like to have 8 by 8 because then we can go down to 200 to 220 millimeter PT slab. But 9 by 11 makes it chunky. It's the first principles which has a cost. The two stairs are linked with a stairwell in the middle here. I'll come back and talk a lot about that one. So the only thing which is making these two towers connect with each other is the stairwell in the middle. So the stairwell is in the middle is the one creating the diaphragm action between the two towers. Have you ever seen that before? The cores are eccentric. We don't like eccentric cores, right? We want to have a lot of gravity load on the cores. The columns, they change shape up through the building from round to blade to back to round. There are huge transfers over here in the bottom of the tower, right? Then we transfer 2 columns out. Why could that ballroom not have been shifted out 10 meters and avoided all that? There are architectural constraints for that. But again, it's just the principles are not just wrong, right? And it creates engineering challenges afterwards. And that's what we'll talk about today. And then of course, all these columns here are 30 meter long, and that's a long column to construct. I have photos of that one. So yeah, I'll just very quickly here, you can see here how the cores are eccentric. So if you drive on the alkyl side, you can see the back side of the core. And of course, the reason why the cores are eccentric is because everything is about the views. And there's nothing to view that way, right, other than the desert. So of course they want all the people to to live in front of the bay so they can view at the bay and at Burj Khalifa. This one is the stairwell in the middle linking the 2 bridges together, 2 buildings together. But I'll come back to that one. You can also see here the round column becoming a blade column, becoming a round column up through the building, and they're all over each other, all the way up to the top, because that was the architectural intent from the beginning. You can also notice that the way that corner column is taken out is actually a transfer the other way. So there's transfers in two directions over this this ballroom here. If we then just look quickly here at the structural system itself, it's the usual Dubai method that we take everything which is there structurally, it will work for lateral stability. So in this case here, it's of course the core wall system with link beams and frame action between floors and cores and columns. And we also have some outrigger levels up through the building. I'll come back to that one in a little while. So yeah, and again, the floor plates do not line up, but it's still one building, everything. We were also discussing about that in the beginning, if we should make some expansion joints and make a little steel bricks, which is just resting on the other one. But that was shot down because of this column theme of the whole building. So if we look at it from a, what should we say, from a modeling point of view, or more sophisticated here, this is how it is. I mean, the cores and the columns and the beams and the floor plates and the beams and the link beams in the core walls itself. Of course, we've done many ETABS models before we found out how it worked. Just a few, again, one of these funny things where you can see how the floor plates, they change from void to void. So this is a void down at 11.7, and this is another void higher up through the building. But again, that column sits on that column, right, as we come further down. So all the PT times cost consultant will come and ask me, what can we do to save on concrete? Yeah, you can shorten the span, right? That's what you can do about that. I don't have a magic wand how to get over that. So it's about getting, if you want cost, if the cores were also not that long, but surprisingly, when we came through the final, or what should we say, versions here, actually the two first mode shapes are in the Y direction. The third is in the X direction, and torsion is actually the fourth mode shape. So this is totally a textbook, what should we say, example, but it's just against one's intuition, because you feel like it should be a little bit more, susceptible for torsion. I thought it was going to be torsion which was going to dominate this building here, but it wasn't. So that's always one of these fun things when you sit and compare your initial thoughts. Okay, if we go to wind engineering, of course we have done what should we say, wind tunnel studies where we model all the surrounding buildings, and you can still see on the yellow shape here that it actually does have this this funnel shape at the dominant direction. So it's facing the Gulf, right, and the Burj Khalifa. And that is the dominant, what should we say, wind direction. So of course we did everything. I mean, the normal wind tunnel study with loads and zone mapping for, what should we say, for the facades, and also the accelerations and local wind environment, all that stuff was part of the wind engineering package. And the way the wind loads were reported was in 3 different coordinates, which we then could enter into ETABS afterwards, and for 36 different wind directions. Now comes the very interesting thing. I'll jump a little bit back and forth. This, where I'm pointing right now, was our initial wind load on the tower, directly out of the code, directly out of ETABS. You can see that from the code wind to the wind tunnel testing, there's a huge difference down. The load is a lot lesser from the wind tunnel test than in our ETABS model. And of course, we know that when we go from code to a wind tunnel test, then we always get a saving of 25% in that range. But I think the main reason for so it's actually, if you can see, it's almost 280% higher, right? The difference between the wind tunnel test and the code wind. So if you remember your wind engineering from first principles, you will remember if you have a straight up and down building, that the upper third of the wind will fly over and around the top. The other 2/3 will have to go down to the bottom where it becomes turbulence and has to crawl all the way around to the building. But because we have opened up so much area here in the bottom, up through the building and rounded the corners, I believe this is part of the reason why we have been able, it's a coincidence, right? I believe this is the reason why the wind load has reduced so much when you compare it from the code. But it's a learning thing, right? It's really interesting, the subject here, how you can actually reduce the wind load by doing these things, because it makes sense that if you look at the middle here, if you are an air molecule, and if there was no voids here, then you have to fly all the way around the building here. First, you have to go down through the downwash, become turbulent, and then around the corner here. Whereas now you can just slip around here. So all that wind load is actually taken off. So that's one of the interesting findings we found here in this building here. It didn't matter because seismic is governing, but it's still interesting in the end of the day here. That's one of those fun things when you can sit and reflect on these things here afterwards. Yeah, if we go to the seismic, then you can see here the base here is 63,000, so it's almost 6 times more than the wind, double the code, and it was in both directions. So seismic governs this building here. It's zone 2B. I think if it was zone 2A, maybe in the long direction, seismic would be governed, and in the short, wind. But anyway, that's what it is. And in this case here, for the substructure, the way the substructure was designed on reaction down piles, we scaled from to basement, and the way the superstructure was designed was we scaled to ground floor. To save money on the superstructure, and this was accepted by the third-party review and also by municipality. Yeah, and if you look at the seismic, there's tons of slides, but the overturning moment is enormous. And if we take a look at the drifts, yeah, they also still comply with code requirements. Now I'll shift the subject a little bit. Sorry, not yet. Next time. So this is the what should we say, the substructure. This is just some key numbers about how many piles we had and how long they were and the concrete strength. And we also had some away from the tower footprint, actually uplift. It's 2 basements down. So there's also tension piles. Again, and there's no expansion joint, of course. And there's also the usual DM temperature calculation in this one here, where everything is fixed. It's being changed now, but so of course a lot of reinforcement is due to temperature in a substructure like this one here. One thing which I'll say also about these types of buildings here and the way what Dubai has become. See how many different types of pile caps we have here. See, and how many different rafts and levels and up and down. This link slab here in the middle is not the same thickness as here. This is called value engineering, some people say. I mean, some cost consultants will call this value engineering. To me, this is not value engineering. This is value engineering would be if all of this was one layer and all of this was one layer. Can you imagine all the amount of processes you have with waterproofing and backfilling and up and down every little way here? It's going to take forever. That's because cost consultants does not know how to offset work processes. They don't know how to offset time against money. And they don't know how to offset risk against money. This to me is not the way you should build. There should be one ref all the way down to there, and also up here. It could also be one big, but if you wanted, you could have a little level difference here. See all the leaking basements we have here in Dubai at the moment. It's because it's complicated to do all this stuff here. I mean, it's not easy to, and the amount of work process you have with different pile cap levels and backfilling and waterproofing, blinding in the bottom, blinding at higher level. Don't tell me it's faster. I mean, you could cast all of this in one day, right? If you have done it correct. Anyway, so there is room for improvement. Buildings needs to be designed by builders, not by commercial people. That's what this is an example of. Okay, so if we look at the cores, of course there's two cores, one in both of the two towers, and it's with link beams. But one of the interesting things we found, or not interesting, everybody should ask this question, because the cores are eccentric. That means that the outer wall, this wall is facing alkyl road, the picture I just showed before. So there's no load on that wall, right? There's no slab load, only self-weight. This is a plot from ETABS in our ultimate model. And we did actually get tension in the outer side. It's not much, only 2 to 3 megapascal. In the service model, there's no tension, but in the ultimate, there is. So if you look at UBC, what does that say? Shouldn't you then go down to 0.35 on your section modifier on your walls when you have tension? I mean, for columns and the core walls, it's said if it cracks, you have to go from 0.7 down to 0.35. We didn't do it because we argued that the modulus of rupture is around 5 and it's an ultimate model. So we sort of agreed with both the third-party consultant and DM that it was okay to just keep it as it is. But one place where you do get punished, right? That's your cold joints. At every floor, the tension cannot jump through a cold joint, right? How can it do that? So of course you have to check. You have to check your cold joints for tension and shear. This is why I don't like eccentric cores, because you don't have the natural gravity load on the one side of the core. Again, I'm saying it's a challenge. This we're back to the Bumble Bee, right? It is possible, but you really need to sit down and analyze these things very carefully, and make sure that that you're doing things right when you have eccentric core walls. If we look at the middle core wall, the link, the one which links the two, it's actually quite surprising that the core wall itself, it changed a little bit from 500 millimeter in thickness, and then I think in the bottom it goes down to 400 or 300. But there's nothing extra in it. It's not like we need to put steel embedments or anything extra. It actually works as it is. And reflecting on this, when I come back to the previous models, to how it is now, and the torsion, right? And how, if you imagine you have two buildings with two different frequencies, of course now it has to have one frequency, but you can imagine that there are some internal forces trying to go each other's way. The only explanation I can find why it is like this is because the core walls are so long in the long direction. So it's actually very, very stiff in the long direction because of the core walls. They are also so long. Because this looks scary, right? I mean, you think about one slab going one direction, one slab going the other direction, what's going to happen right here, right? But it was actually just to, not just, when we designed these core walls, straight out of ETABS, there was no surprises at all. A few, so where the core is visible, it has this shape here. And at the floors, if you imagine you come up to the stair and then you have a corridor down here to the hotel room, there was a little bit reconfiguration of the stairs in this area here. So why is this one here important? There's two interesting things. First of all, it acts as a link between the two buildings structurally. But if you notice the drawing before where we had the drop-off zone, so Foster's and partner actually wanted to transfer this this core wall out at level 4 and say it stops there, doesn't go down to Mother Earth. And DM or Civil Defense, I don't know who it was, would not allow it. So we had to, structurally, of course, it's logical that it has to go down to the raft, and it's good because it just makes sense. So, but they actually wanted to transfer it out. It's not impossible to transfer it out. I mean, you can do it. But the reason why it looks like it does is actually because that, okay, there was a stairwell here, and DM said all stairwells must be concrete, and they must go down in one straight line to the raft and up to the roof. That's actually why it looks as it does. And of course, as a structural engineer, I'm actually happy we have this one here because it ties the whole thing together, and it would also be a nightmare to transfer that out. But can you imagine all the coordination we have down in that drop-off area with all these columns and all these core walls coming down and all this activity of people coming in and out, because we didn't want to have a transfer. That was sort of the philosophy behind the whole project, is no transfers. Except for this wish about trying to get rid of that stairwell here. If we take a look at the columns, this is one of the views of this is the hotel side, where you have the ballroom underneath these raking columns. If you look at the ETAP model, you can see that the columns center lines, they line up until they meet a frame element. This, of course, is an architectural nightmare because an architect would like all the front faces to be out at the facade line. The reason for this was that DM said that an offset in a center line is a transfer structure. And DM will only allow one transfer in one load path. So you cannot have a transfer on a transfer on a transfer. They would not allow that. So, for example, if we take a look at that level here, it's okay. Here we could play around with, so they would allow one level where we cut off and say, here we move the column faces out to the facade, but the rest has to go straight up. So first of all, we had to make sure that all the columns were in the right location with all the room and the drop-off level, but then we would also have to look at it in the building in that direction afterwards. So some of these areas here, you can see in the top, you have a round, you have a blade, you have a round, you have a blade, you have a round, all the way down. As long as that is in the same center line, then DM was happy with that. I'll come back to how we did that. Okay, so back in the day when we were doing a lot of projects in Index and residences and around here, we also had, if you imagine that you have one blade column and another blade column on top. So you would have two blade columns, but they change direction. You can make like a transition element or a huge core, right? Call it whatever you want to call it. So what the way we convinced DM to do these transitions was that every time we have a change between a blade and a round shape, we will introduce these transition elements. You can see them here to catch the what should we say, to get the load from one geometrical size into another geometrical size. You can also see them here. We will also show some photos now. So the agreement was that center line must line up until the first time you have a transfer, and every time you have either a transfer or what should we say, geometrical change, we have a transition element. That was sort of the agreement and why the building looks as it does right now. So for example, one transition element, so you see this one here, the round blue column sits perfectly clean over the blade column underneath. And there is a transition element which makes sure that all the forces get from one geometrical size into the next one. You can see on this plan here, this is another case where the columns are shifted out. So the outer face of the circular column matches with the blade, and that's now a transfer structure. All of these transfer element, transition element, these ones all have omega factor on top of that. And of course, because we have high strength columns, then all the transition element is the same concrete strength as the column. And yeah, an omega factor on everything. So that, of course, there's a lot of checks you have to do when you do these ones. You have to check the bearings as simplified strut and tie model. We have to do the mushrooming, which is the concrete strength, and of course the omega factor. So that's sort of the agreement we had with both third-party review and also DM. So this is how it looks. I mean, inside the voids. And if you look up here, you can see the dark concrete is actually the mushrooming detail. That concrete strength is the same as the column concrete strength. You can also see them over here, all these mushrooming details. Every time we have the column running through the slabs, we have the mushrooming. And this is how it looks through the void. It's quite amazing. I mean, last year, 1 year ago, I uploaded these 3 images on LinkedIn, and they got 65,000 views. It's the highest I've ever had on any of my uploads. So people must like this. I mean, so I think the architect hit exactly the right impression for the building here. If we come to see how we actually built these, what should we say, the round columns which are in the voids. It's actually like a steel tube. I think they're like 4 to 5 meters in segments, and then they are welded together, and then you insert a reinforcement cage inside the tubes. And then of course, yeah, they're welded together, and then you just build up until you reach up to where they end off. So it's like a 30-meter tall composite column, and it also has internal shear studs at the upper and lower 1/3. And beside of doing ETABS model, we have done tons of manual calculation of what happens when you have wind on it can actually be quite governing if you only have wind on a circular column like that, an earthquake and delta, all sorts of manual calculation to convince yourself that it works. One thing I will say about this one here, which again, back to building physics. So in this approval process, Civil Defense and Dubai Municipality said that these columns here need to have a 3-hour fire rating. Okay, so if you look over here and say if there is a fire, why do you need to have 3-hour fire rating on any of that? Well, I simply don't understand that logic. And also, I mean, why not just have a robustness analogy? So anyway, these columns here has been fire painted with a 3-hour fire rating. So you have a concrete column, you have a steel tube, and then you have fire rating. On paper, Dubai Municipality and Civil Defense do actually say they accept performance-based fire engineering, and that's what I think should have happened here. What I also think what should have happened here was that this is a thermal bridge, right? Bang, man. We just saw the balconies before, they are insulated. So why is the column not insulated? In my mind, you should have had that column, and then you should have insulated it and put a nice GRC cladding around. Building physics, right? This is building physics, and that insulation could actually have been fire rated, right? I mean, you can get these canal for whatever. There are Rockwell products which can perform the fire rating, and then you would also have not so big a temperature difference as you do right now. I don't know how these MVP guys they actually model that, but this is a thermal bridge up through the whole building. So yeah, no, this is to me how it should have been done. But that's also this is Dubai, right? We have compromises all the time, and we have to live with that. But as long as if we don't question it, we will not improve. And this is why I'm questioning this at the moment. So if we look at some of the outrigger levels, we have in the lower building we have one outrigger level, and in the taller one we have 2 outrigger levels. And so, yeah, that's of course the logical reason for that is to minimize the sway of the whole building. And when you get that into place from the concept phase, of course you will get a lot of savings in other areas. I'll just go to one of the to the taller building. Here you can see the outriggers. So it's all a mechanical floor. For example, this line here, you can see this is the lower level. And then when we come to the upper level, the outrigger sits in the same line. So it's the same column, which gets the smack from the outrigger. And of course, also the omega factor and all that stuff. And they're all located at the mechanical floors. And so this is a snap from the ETABS about how one of the outriggers look. And what you can't see is that because of these huge openings, we actually had to create some flanges in the top and in the bottom at slab level, and some were even thicker than the floor slabs. So if you imagine, it's like a huge I-beam which is cast into the whole outrigger here. So this is just one of the. This is not the real thing. It's just an image about what happens when you have outriggers in concrete. And this is the amount of steel. There you can see the flanges, right? This is what I call a flange in the floor slab, top and bottom. So it is like a huge I-beam with flanges with openings in the web, you can say, to make that work. These outriggers. And took these photos in February before the whole world collapsed. And this is how it looks. And again, I mean, I'm not going to sit here and sound provocative, but I mean, this is again when structural decisions are made by commercial people, this is what happens, right? Because they look in spreadsheets and then they say a concrete outrigger is cheaper than a steel outrigger. To me, if you have had a K-frame with a bar with a steel trot here and up there, and then you would have just like that, and you would have even more space to design all this stuff and to build all this stuff. I don't believe that it's cheaper. I simply don't believe it. And if you had a steel truss, you could actually, all the sequential construction stuff, you could actually loosen all the bolts afterward and that the building settle a little bit and then tighten it afterwards. To me, when you have things like this should actually just be a steel structure. Like 1, 2, 3, 4, 5 beams, that's it. But again, this is when the wrong people are running the decisions, then these things happen. It's my opinion. Other people can have other opinions. Yeah, so if we look at this transfer structure here where we have the ballroom. So again, here you can see that it's actually 2 columns which are being transferred out in that corner. The reason why we did it over here was simply to make it symmetrical so it looks nice. So if you look at the framing at the end of the building, it's the 3 columns, which then one disappears in one direction of the whole thing here. So that's the reason why we did it. But it's very, very big forces coming down into these corners here. So the whole, what should we say, transfer truss, which it is, it's actually a composite structure, but not with a tube, but the other way around. It's with an embedded steel structure inside the concrete. So it's the other type of composite structure than as we know it. And here you can also see these transition elements sitting up here underneath. In the other direction, it's the same thing again. Here we also have steel inside. And just to give you an idea how this arrow is actually the wrong direction, it should be out. Just to give you an impression about how big the forces are, I mean, being transferred out. So these are the compression 23,000 kilonewton in the column. And what so what was interesting in and also back to my little hiccup before, right? All these columns here are outdoor, actually sitting outdoors in front of the facade, so you can see them, and they're not insulated. So if we take a look at what happens at this level here. So all these columns, so underneath here is where we have the raking columns. So that column is, you have a raking column backwards, and that column, you have a raking column that way. And that generates insane amount of high forces in these tie beams. And that's why we have these thickenings. You can see how much thickening we have done around here. Actually, the first proposal we actually did an embedded steel truss inside the floor slab. But as we came closer to in the design and build, I mean, in the detailed design, it was actually possible to convert all that steel into a conventional, reinforced plate. So, which of course also acts like a truss, but everything is then, concrete. So to get all those forces back into the core wall, there's you can imagine that this is like a truss system which carries the forces back up and then in here. And of course, the cold joints here are, it's amazing how much reinforcement we have just to get those forces back into the core walls because of the magnitude of the forces. Anyway, super interesting, and all of these, both the transfer themselves, the raking beams and the ties, are all designed with the omega factor as transition elements. And here you can see, for example, how one column is transferred out. You can also see all the transition elements here, the tie beams, how it looks in real life. It's actually, if you want to see it, you have to go there now because the facades are getting erected at the moment here. I'll just show you one more here. You can also see it is very, very amazing structure. I mean, it looks fantastic. And again, these transition elements, tie beams going back and forth. There you can also see it. Here you actually have a bit of the facade being constructed. I think this is the trial room or whatever they call it. And then we've also been through the construction sequence analysis, and it does have a little stomach there on the middle, trying to bend a little bit out, which is also as it should. I just want to touch a little bit. The last topic here is about diaphragm action, and I think one of the big learnings here is that it's logical that when you have columns which are raking, for example, that you will have forces in your. So when you sit with your first principles and you design these things, you know that. But the thing is, how do you practically design with the tools we have today? How do you remember to take into account all these forces here? Because usually a lot of these floors will be a PT designer who does it. So PT software and SAFE does not know how to take into account the lateral loads. So it's all establishing all those principles about who designs the diaphragm action, who designs the ties. It's a little bit the same as when we have a temperature and gravity loads. I mean, who tells the PT designer what extra reinforcement is to be put where, and that's where you really need to concentrate to find out, because some of these forces are very, very big, and it seems counterintuitive that you have tension forces and then you have a PT slab afterwards. I mean, so you really need to think about what happens in diaphragm action when you have a raking columns, and how do you tie the forces back to the superstructure. So anyway, this is just one of the learnings and findings, that it can be some very, very significant loads which can occur there. I will just show you. Yeah, we already talked about that. This is where we have that truss. So this is how it looks today. If you drive by, I think this picture is probably a couple of weeks old. So the facades are being installed at the moment, and some of the views from how it looks from a finished room, it looks amazing. I mean, it's fantastic. So January 2020, when everything before the Corona crisis, and there was going to be all these seminars and CTBH and whatever, I actually submitted this project here, and the one I showed you before with these balconies with big. I submitted those to CTBH, to the one in Singapore, as possible presentations. And they came back to me and said both of the projects were too ordinary, they were too boring. And afterwards, they have changed their mind, because now the whole Corona crisis have turned the world upside down. So they have asked us to write an article about the one I showed before with the building system and the facade and the balconies, and that's actually being that will come in one of the next CTBH journals. It's a 4,000 word article with pictures and illustrations. So yeah, the Corona has really done a lot of things this year here. So I was actually happy when I was asked if I wanted to present this, because I have a lot of thoughts about it. So now I have the presentation is done. So it's there. And then the last slide here is just so you can see how it looks from inside one of the rooms and out into the bay itself. Yeah, I think that's it. I think 1 hour, right, Sam? So yes.
That's excellent, Jen. Yeah, I think you have pampered too much architecture. I can see that. Is it that client requirement to have such a complex structural system, to have so much changes in the vertically?
This was actually it's you can say it's an architectural intent, but yeah, there's always a relation between when an architect has a vision. If the client likes it, it comes from there, right? And you simply can't get it out of their heads afterwards. And then it becomes a challenge, right? Then it becomes an engineering challenge to try to make it work. And this is the fun part of it. I mean, and the challenge. Yeah.
Yeah, Jens, we have a few questions actually. It looks your presentation is very well addressed to all the audiences. Okay, a question from Vijay Singh.
Yeah.
In the long columns, if you don't put I sections instead of circular steel plate, would have saved in paint cost, and would have helped in a better way. What are your comments on that?
Yeah, I mean, yes, there's three options, right? One is just concrete. The other one is composite with steel in the middle, and the other one was the tube. The reason why the tube was made was due to buildability, right? Because if you imagine that you put one tube and it's fixed, and then you come with the next one on top, and you can weld it. Now it's stable.
It's a form work, basically.
You don't have to form it up. So the tube itself becomes the form, and then you put them on top of each other. That was it all comes down to what should we say, the contractor, and I'm sure you will have two contractors who has different opinions. But this is what it ended up with this contractor. Right? So yeah.
Another question from Mr. Callum. Did you consider not using PT slabs in the transfer zone to not to have mixture of design ownership?
Yeah, if you ask, yes, yeah. If you ask me, I really get so nervous when I see a PT slab where you have these forces in and out. I mean, to me, all of that slab. This was also why in the beginning, at that level, we actually had an embedded steel truss, a horizontal steel truss, right? So we get completely out of the discussion. There's a direct load path from the columns into the core walls. I don't like it when you start using PT slabs and raking columns. I mean, it just seems so counterintuitive. So I would also prefer to do it in situ. Yeah. Yes.
So basically, in addition to that statement, if you would have provided PT generally for the dead loads, vertical gravity loads, yeah, would have designed with a vertical system or gravity loads for the PT, and if you're given your system as separate, it would have been design ownership is clear, I think.
Yeah, yeah. That is the practical version. I mean, where we had just the small transfers. The way it's done is that the PT designer does his for gravity load, and then we actually go and override it afterwards and say, okay, now we have a transition element, and that has to be able to transfer the load back into the core manually calculation. But that's one. My point is that it's really important not to forget these things, but it's some huge forces you can get in the floor plate.
Yeah, but again, secondary effects also, what going to be secondary effects? Yeah. Yes. There's a question from Nishant Rathi. Could you explain load path at the transfer from blade column to circular column?
Yes, I'll just find that.
Yeah.
Just a minute. So the way it works is that, see, this is the one. For example, here, this is a blade column sitting on a round column. So here you have a rectangular shape, and here you have a round shape. So that means all these, it's like a two-dimensional truss which you need to generate from one shape to the other shape. And you can do that manually, I mean, and find out what happens. But so usually you can also compare it, if you did that upside down, then you can compare it to a corbel, right? So you'll get tension in this bottom layer here, because you're trying to squeeze out one geometrical shape into another shape. So it is like the primitive answer is it's just like a corbel, but it's in 2 dimensions and it's from blades to round, right? So if you imagine you have 2 blades, it's a lot easier to say, okay, how do I get those forces from one shape to the other? But because it's round, I mean, you have to model that to see how the forces come around. And then you have the thing with the bearing. And then when you start looking at bearing, you have this A1 and A2 stuff and all that, and get into all these things. But this is the philosophy is that you need to draw a line from here out to there, all the way around, and see how that cone shapes. Yeah. Is there enough compression strength, and what outer forces do we then get because of that? That's the explanation.
Oh. Yeah. There's a question from Mr. Kevin. I think he's working hard and he's interested in your topic. He's from Australia. The question from Australia at 2 a.m. Do you think the mushrooming was strictly necessary for this job if you are not a DM requirement?
It's you can say, first of all, if you do it, it's idiot proof, right? Then you don't need to worry about it. But I agree. I know what the thing is, because it comes back to this A1 and A2, because it's about aspect ratio. So, for example, the old rule of thumb was that the old rule of thumb in DM was that when you change a strength, it should always be maximum 10 megapascal. Because then you could always make it work with these A1 and A2. If you change 20 megapascal, then you need to go and check all these things and add reinforcement in. So yes, it could probably have been possible not to do mushrooming in some areas, but it would have required a lot more of checks and extra reinforcement to make sure that confinement would work in that area. So yes, it would probably have worked, but you can say the other solution here, where we have the same concrete strength all the way down, it's it will work, right?
Yeah.
Just because, yeah.
It's a bit long question, but I'll just put it short. A question from Krishna Prasad Menon, most probably is from Kuwait. Question is, in the first institution, you think it's a torsional mode, but where it's not. What is your thought about that?
Okay. This is because in the beginning, it's because I'm also mixing up the concept states. So the first two is Y, X, and the last is torsion. It's because when you look at the building intuitively, when you see this, it looks very weak, right? So you think that the torsion will be governed. I think that when I look at this, it looks like it will be torsion, but the reason why it's not torsion, it's because these cores are so long. Yeah. It's a very, very long core wall. I don't know what the aspect ratio is, but and it is very, very stiff in these directions. Yeah. So yeah, but yes, I was also surprised that that the torsion was not governing. I mean, in the end. So yeah, well, good question. I mean, yeah.
But you have a big course, yeah, as you said, yes, correct. It's a question from Mr. Hemant. Your punch dialogue, you said buildings to be designed by the not cost consultant, designers, the same question. What was the additional reinforcement added because of all the reinforcement, because of all this complexity? What is the percentage of reinforcement extra added for vertical load path because of challenges which you have?
Don't think there's anything with load path, but this is the thing. If we look at, for example, this one here, when it comes to cost consultant, right? Yeah. The cost consultant is right. This is possible to squeeze it's a pragmatic view, right? So the cost consultant is correct. This is the optimum. This is the optimum size of concrete and reinforcement, and he can now take his spreadsheet and he can go to his boss and say, I have now optimized this substructure. But to me, that is called sub-optimization. He's forgetting the big picture, because if you sub-optimize concrete and hurt processes and blinding levels and backfilling and waterproofing and risk and time, and if you're not able to offset that, are you then a good cost consultant? It's the same thing with outriggers. It's a principal discussion. Sub-optimization always has a bad effect on other trades. That was my point. Yes. Oh. So it's actually the other way around. He has saved money here on, if you only look at concrete and reinforcement, yes, he's correct. He optimized it. But I don't agree to that way of thinking from a big picture. Yeah.
Yeah. I think there's a question from Sir Raghav Sharma. At the raking column locations, you have provided steel reinforcement to compensate the tension. What about the plain buckling of the slabs at the last bay due to high compression?
Oh yeah, all that sequential stuff is also analyzed. There are some huge, I did show that, didn't I? We have a sequential construction model also. So all of these, in the end of the day, all the load combinations which are, being designed for is a sequential construction load case. So all of those differential settlements, column shortening, long-term creep, all that stuff is in these load combinations. I don't know what the number was, I don't know, but it is taken into account.
Okay. Yeah. A question from Inbad from Singapore. What was the percentage of column stiffness taken in the PT floor design? I'm not sure what is the question. I'm not clear actually. What was the percentage of column stiffness taken in the PT floor design?
The column stiffness is in the ultimate model. We use the usual 0.7. Yeah.
Anything maybe because of high horizontal forces, did you consider maybe less or more? That's what maybe is intention. What is that?
No, we did some. We actually in another presentation we have done. I can't remember what it is. We found out how much of the lateral force is actually obtained by the traditional framing and how much is taken by the core. I can't remember the percentage, but it's probably that what he's coming from. Yeah.
We take another 2 to 3 questions. Yeah. There's a question from Mohammed Ushari Kumaral Effendi Mohammed Yusuf. What is the highest grade of concrete used in the project, and how you control the temperature?
This is concrete 90. Concrete 90 is the highest. You can see it here. So this is cube. So you have to multiply it with 0.75 if you want to get it into, as a rule of thumb, if you want to get it into cylinder. So what I have shown here, all these concrete strength is cube. And I mean, we didn't do anything about temperature. The only thing is that the raft, of course, you use GGBS, right? Yeah. To try to extend the curing time. I mean, so constructing in these type of concrete strength is common practice in Dubai. There's nothing specially done. I mean, you have normal standard procedures how to do the casting. And I mean, if you're a good builder, right? The good builder with the boots on a summer day, right? What he will do is he will go out and he will spray all his reinforcement so it almost becomes moist, so he cools the reinforcement down, and then he starts casting his raft, and then he puts GGBS in. That's a good way of doing those things.
Okay.
Yeah.
What is the possibility of using GFRP reinforcement in the raft to avoid congestion of reinforcement? It's a bit different question. It's a question from Mr. Mohammed Izzat. Maybe he's thinking about high strength rebar, maybe.
Yeah, well, I don't think it's that popular here in UAE, but elsewhere around the world, there are mixes that you can actually replace some of the conventional reinforcement with fibers and not the strength, right? It's about crack width and durability. For example, in my home country, it's used in many places. I mean, especially in substructures for that one, and that's simply to save on labor, save on reinforcement, and actually it gives also a better durability by mixing that in. So yeah, it's not popular here. I don't know why.
Yeah, that's true. Yeah. Again, question from Mr. Callum. How you casted 30-meter length columns? What is the construction sequence not to segregate concrete, etc.? What is the
So again, it follows these. Where is it? See, so each section, each tube is about 4 to 5 meters long. Then there you can see the horizontal line here. That is where they are welded. So you come with one tube, place it on the other one. It has bars sticking up into the other tube. Then you put your, and it's already cast up to here, right? And then you put your reinforcement cage inside. So you only cast these 4 to 5 meters per sequence. That's and it's purely down to buildability, right? Yeah, how do you construct a column like this? So it's not like 30 meters is cast in one go.
Even 4 to 5 meters 4 to 5 meters is too high, I believe.
Yeah, maybe it was 3 or 4. I mean, something like that. You can actually go and see it. Yeah. But this is purely about constructability. I mean, just to go up there. And then as soon as you have done that and it's welded, then it is stable, right? And you can actually build your scaffolding around it as you go up.
Yeah. Again, a question from Singapore, Mr. Inbad. How did you prevent disproportionate collapse in the areas near raking columns?
Yes, this is really one of my topics. I can talk about that for 15 hours. And because we didn't, right? My philosophy is that, for example, when I was making fun about these columns and fire before, right? To me, the right way, very right way would be to make a performance-based fire study here. Is it actually possible that if you have a fire in an open void that you can actually even get up to 3 hours? Don't believe that a sofa burning in here can burn for 3 hours. I simply don't believe it. So that's the one thing, is to make a performance-based fire engineering assessment. But I also believe that there should actually be a robustness requirement for high-rise in UAE, where we remove key elements. For example, what would happen if we remove that column? Is there then an alternative load path? It probably is, right? Because everything is in theta. And it's correct. What happened if that one collapses, if somebody drew in? So I fully agree that that has to be, what's it called? An authority requirement. And I know why it's not. It's because we're using ACI today and the UBC, and ACI and UBC has a lot of inbuilt robustness thoughts. Why do we have this continuity? All those things. But it's not like, for example, if you look at the Eurocodes, where it says buildings more than 15 meters must have an alternative load path if something collapses. Straightforward. Now you know what to do. And you can't find that in the DM code. You can't find that in the ACI code. And then you can say, should we as engineer impose this on the building? Yeah, that we can discuss elsewhere. My opinion is that you should design for progressive collapse, because progressive collapse is the same. So first, if you design a building and we say we have the load factors, okay, that's one layer of safety. The next layer of safety is to say we appoint a third-party reviewer for buildings which is taller than something or whatever. So that's another layer of safety. And I believe that the third layer of safety should be that these sorts of buildings here should always be designed for progressive collapse. Those three levels of safety should simply be there, and they're not. They're not. There are no requirements in UAE for progressive collapse. And of course, if you have very big transfers, it's impossible. How can you have a transfer which is resting on two columns designed for progressive collapse? Because it will collapse, right? So, but then you must do other things, right? I mean, you have to think what's going on.
Yeah. Passive protection. Yeah. The question from Sharfuddin, your old colleague, I believe, is asking a question. If you use a K-shaped steel structure, maybe economical instead of concrete wall, maybe it'll have effect in a drift, you know.
Say that again. I didn't get it.
No, if you, one of your comment in the presentation, you mentioned if it would have been steel structure, it would have been economical.
This is what I'm saying. I mean, I don't think this is the outrigger. I don't think this is the right way to do an outrigger in this case here.
Yeah, maybe if you change to steel, maybe a drift, maybe a problem. That's what his thoughts. What do you think about that?
Maybe it will be more costly or what?
Yeah, if you propose.
This is exactly the same example as the foundations, right? That in the spreadsheet, it probably looks like this is cheaper to do in concrete than steel, but all the associated things and checks, and I don't know what happens here. This takes forever. If you look at these reinforcement drawings, how horrible all this is, and we have to do flanges in the slabs afterwards. The amount of time to coordinate this, and also the coordination, right? If this had been a K-frame, bang, bang, all that area is up to the MEP, right?
Yeah, that's true. No doubt about that. Steel is definitely better.
Yes.
And we got a different trade, basically. Yeah.
Yes. So.
Because in this part of the world, the people think concrete is best solution, you know, everything.
Yeah, it's because it says in the spreadsheet.
Yeah, I think we'll take two questions more.
Can we take it from the YouTube channel, because we have like 25 viewers?
Yeah, please.
Yeah.
We'll give preference to them. Yes, agreed. Yeah.
So I believe like many people are saying like great presentation. Thank you, Jens, for the perfect presentation. And so usually the good presentations comes with lots of questions, as you can see. So the question here is from Nitish Raut. Question for the incline transfer columns. I could not see any tie member at top floor levels. Is the slab taking the tie forces from incline columns? And the completion of the question is, and has this been designed for omega of 2.8? Yeah.
So this is the plan. All this slab here is designed with omega factor. So underneath here, underneath this column here, that's where we have a raking column backwards. underneath this column here, that's where we have a raking column backwards. We also have it down here, but that's because of symmetry, so it looks the same. So of course, when you have a raking column that way, a raking column that way, that's why we have these huge tie beams here. I can just go one slide back. See how big it is. So all of these tie beams here is actually the ones which is framing up all these forces here. So to take care of these forces acting in this level and here, that's actually what these tie beams are doing and bringing the back into the core. This is what I'm saying. In our first design, we actually had a steel truss, horizontal steel truss sitting here, embedded into the concrete, doing exactly that, bringing the forces from these inclined columns back into the core. But now we've converted into these tie beams here. So that's how it's taken care of.
One more question. Yeah. It will be the last one because we still have 3-4 minutes to go. The question says, sum of mass participation first 2 modes is more than 100%. May 2 parts are behaving differently in the same model. Can you please explain?
That I don't know. The point that was not the point. The point was that it was torsion which was not governing, which intuitively you would think, right? What was that one? Because I also have another model where it was 3, where it was what is that?
Yep.
Yeah, okay, that's a little bit here. But anyway, the point is that it's not the first. The torsion is not the first mode shape, which you just feel it should be, right, when you see it. That's sort of the fun engineering part of this, I think. So yeah.
Yeah, Abdullah?
I think that's it for now. Like otherwise, like everyone else is saying, like it's a great presentation.
I think we have 2 minutes. I'll take one more question, last question. I know this building is very complex. You must have spent good design man hours. So how much time a client allowed you to design this project? You got a...
it was quite far. As I said, I mean, this is 5.5 years ago when I came. This was on my table, right? And you can see how far we are right now. It's still under construction. And I mean, by doing this presentation here, I was looking through the numbers of revisions, right? I mean, it's like 18 revisions of, no, because there's been, if you imagine that, because first you do a concept lab, and in the design phase, when the operator gets appointed, the operator will have opinions about room sizes, they will have opinions about all these things, and then you have to go through everything one more time. And then that's how it is. I know that it's quite funny that I come from Scandinavia, which is an area with consensus, and we have to discuss everything over and over, and it takes forever. But that's only discussions, right? So for example, if you were to build an area with towers, oh man, you would discuss this for 10 years about how they should look and where they should be. But as soon as it's decided, it will be constructed very quickly. Whereas here, we just start without having know who's going to buy it, who's going to this, and then in the middle, oh, the market is changing now. I need an office tower instead, and that's why it takes forever here, right? It's simply 2 different fundamental reasons, but it takes forever both places in the world to build these huge projects here. So yeah.
So we must say thanks to your client providing 5.5 year service for you. You know.
Yes.
Good. Thank you, Mr. Jens. Thanks for your time. I think this is a very pleasure to see you yearly basis. Every year we'll give a one talk. It's a great privilege to provide a platform for you. Actually, looking forward to see you similar talks in future.
Yes.
And friends, we have next talk maybe in 20th of this month. Next month, sorry. That will be even equally interesting topic for you. It's a sky views, maybe most probably. That's about next topic, and that's all for today. And today, Mr. Abdullah, thank you for your technical, as usual, technical brain behind arranging the talk. Myself,
thanks to Jens for such a great presentation.
Yes, thank you.
is
Thank
really
you and
intense. Yeah.
Okay. Yes. Yeah. Thanks.
Yeah, thanks and God bless you. Take care, everybody.
Yeah. Thank you, everyone.
Yes. Thanks. Bye.
Yeah. Enjoy your evening. Bye bye.